Good afternoon all. Myself Rajit TJ. Good afternoon all. Myself Rajit TJ, Assistant Professor, Department of Civil Engineering, Vidyavardha College of Engineering, Mysore. I welcome all of you for the session 1 of day 7 GET training program on subject Hydrology and Irrigation by Professor Madhushree C. Professor Madhushree C working as Assistant Professor, having over 5 years of teaching and research experience. She obtained her bachelor's degree in civil engineering from PS College of Engineering, Mandya, and master's degree in hydraulics from the National Institute of Engineering, Mysore. She offers consultancy services related to water resources and irrigation engineering. In today's session, she will be speaking on hydrology and irrigation pertaining to GATE 2021. With the short note, I request Professor Madhushree to take over the session. Over to Professor Madhushree.
Thank you, Professor Rajit. Good afternoon, everyone. Welcome to the second session of hydrology and irrigation. So in the previous session, that is yesterday's session, we had finished a few topics. We had discussed the syllabus. I'll just brush up whatever the topics we had covered in session 1 so that it will have some background for you to understand what are the topics we are covering in this session. So in the previous session, we covered the topics related to precipitation and its measurements. We had seen the topics related to mean precipitation calculation, missing data calculation, and other stuff. So we have to see through the hydrographs topics, which we'll complete it in this session, and also groundwater hydrology and flood routing. So, and also we have to take up a little bit of topics related to irrigation. As discussed the syllabus in the previous session, these are the topics in irrigation, but majorly we'll be concentrating on this first topic, that is water requirements of the crops. So majorly most of the questions that will be asked in this particular topic, and the rest of the 3 topics are related to design topics. So, and hence it's not more likely asked in the GATE examination. So we discussed related to the strategy of marks variations for hydrology and irrigation over the few years. And with this, we concluded that hydrology is of much weightage, and hence irrigation, I've covered only a few topics where it is most likely to ask. So with this, we took the high weightage and low weightage topics here. So the last part is with respect to design, which will not be discussed here. So the rest of all the topics related to hydrology and irrigation has been discussed. So I'm just brushing up what we did in the previous session here. So in the previous session, we completed all the topics related to precipitation, which was divided into these concepts, where we discussed related to the theory part of precipitation, forms of precipitation, hydrological cycle, and then before moving on to the problems related to calculations of optimum number of rain gauge, we studied some theory part related to rain gauges and how the site selection should be made for the rain gauges and what are the different types of rain gauges, and how do we calculate the optimum number of rain gauge and what should be the formula to be adopted and what is the key point. So the next thing was related to missing value calculations. Here we discussed the 2 methods, that is simple average and normal ratio method. So here I had given you the hint to follow how to decide the given numerical problem to adopt new simple average or normal ratio method. So that we discussed here. And the topic we discussed was related to mean precipitation, where there were 3 subcategories of mean precipitation. One was arithmetic mean, Thiessen polygon method, and isoheital method. So I had discussed arithmetic mean, which is nothing but a simple average method, and Thiessen polygons have discussed all the related basic figures and how to solve it very easily. So we had discussed square, triangle, and if you have one more rain gauge station in between, the corners of the rain gauge stations also we had discussed, and the one more was a combination of rectangle and triangle, that is a pentagon we discussed, and I given a numerical problem for you people to solve and put the values in the chat box also. So the last part which was left out was mass curve and hydrograph, which was discussed with a combination of infiltration. So these were the topics when related to infiltration, where we had discussed related to evaporation, mass curve, hydrograph. And I said energy balance equation is also included in the infiltration, but it is of less weightage, and hence we concentrated only on these two, that is mass curve hydrograph and water budget equation. So while coming to the infiltration concept, so these three concepts are very much important. That is Horton's equation, W index and phi index. Here I discussed in the previous session how to get the rainfall depth or the infiltration depth with respect to the Horton's equation, that you have to integrate the Horton's equation. If you integrate Horton's equation, you directly get the infiltration depth. And then we covered the topics related to W index and phi index. I had given you the hints when you have to consider phi index and W index as same, or when you have to adopt a different formula. That is if it is a uniform intensity of flow or a uniform rainfall depth is given, then you go for phi index, which is same as W index. The formula remains same. But if the rainfall depth or the rainfall intensity is non-uniform, then you have to first calculate a W index, then check whether the rainfall depths mentioned is within the range, or does it exceed the W index value. So you have to consider only the exceeded value or the effective value to calculate phi index. Rather, the formula remains same, but the difference is in W index, you include the complete precipitation data, whereas in phi index, you only consider the effective data. That is, the values which exceed W index, you take only that part of precipitation data. So we covered that. So the next part is, before moving on to the groundwater hydrology, I discussed related to flood routing. So we discussed what is flood routing and why this technique is used majorly. So we discussed it is mainly used for the flood forecasting, protection works, design of spillways and reservoirs and stuff. And we discussed also different procedures for flood routing, reservoir routing, and channel routing. And again, the models to build up for this procedures is divided into two categories, that is hydraulic routing and also hydrologic routing. So we discussed and what are the how do you identify or how do you bifurcate between hydraulic routing and hydrologic routing. So hydraulic routing mainly comprises of equations of motion and also continuity equation, whereas hydrologic routing, it is mainly based upon only equation of continuity. So we dealt with what are the important terms that you have to remember related to flood routing or calculating of frequency of flood occurrence. That is standard project flood, probable maximum flood, and design flood. These all indicate the values for the severe conditions of meteorological conditions or hydrological conditions of a particular dam. So all these three includes the severe conditions. That is the ultimate estimate. So again, there are different methods of calculating for reservoir routing as well as channel routing. So reservoir routing, you have two methods, Goderich method and modified pulse method or storage indication method. We had discussed the formulas which is adopted in these two methods. And then we discussed related to methods of channel routing. Again, there are two methods here under channel routing. One is wedge storage and prism storage. Again, for the wedge storage, we discussed what are the formulas to be adopted. And one most important thing you have to remember is for the total storage capacity for the channel routing, which depends on the shape variations, M, that is the constant, exponent constant, it varies for the range of 0.6 for rectangular channels, whereas for any natural channels, the value of M is nothing but 1. So in the given numerical problem, you can easily decide which values you have to adopt if not M value is given. Then if it is mentioned as rectangular channel, then you can directly adopt 0.6 for M value. If it is not specifically mentioned, if it says any natural channels, then you can go for M value as 1. So one important equation that you have to remember is Buckingham-Routing equation. So here the methods of flood estimation we discussed, there are different methods, rational method and empirical formula method. We discussed this in the previous session also. The rational method have given the formula when to adopt it. So this rational method is adopted when the catchment area is less than 50 kilometers square. So empirical formula method, you have again three bifurcations in empirical formula: Dickens formula, Ryer's formula, and Inglis formula. Again, these three subcategories of empirical formula, it depends on the regions. So based on the region mentioned in the numerical problem, you can decide which empirical formula you have to adopt to calculate the peak discharge. So before moving on to the probability methods, here we had again one of the different methods for the flood estimation we discussed related to unit hydrograph and probability method. Again, in the probability method, you had two categories, that is statistical probability method and also theoretical probability method. Theoretical probability method is also known as Gumbel's method. So statistical method you adopt when the sample size is more, and you adopt Gumbel's method when the sample size is small. Okay, so here I had taken a simple problem to explain the water budget equation. How to identify the given numerical problem, whether it belongs to water budget equation, was if in any numerical problem, if the difference in water levels are mentioned, then it obviously belongs to the water budget equation, which simply says that inflow minus outflow is equals to water level. But here, what you have to be very careful is, if they have asked you to calculate the runoff volume in terms of, that is meter cube, you have to keep all the terms in meter cube only. So if you, the values would be given in the numerical problem in terms of depth, in terms of meters or millimeters, but you have to convert it to the meter cube, that is volume, by multiplying it with the area value. So that is most important. The next important term was related to evaporation. So the actual evaporation is equal to pan evaporation into coefficient of pan. Here, irrespective of any type of measuring instruments used for the evaporation calculation, the coefficient of evaporation, that is pan coefficient, should be taken as 0.8 itself. So please adopt 0.8 for irrespective of any instrument used for the measurement, actual measurement of evaporation. But here, one thing you have to be very careful, that the left-hand side should be equal to right-hand side. The unit should be same, and it should be mentioned in terms of depth-wise, either in centimeter, millimeter, or meters. So both left-hand side units and right-hand side units should be same, and you multiply it with the coefficient to get the actual evaporation. But while substituting here back to the water budget equation, you have to remember that it should be in volume. So the depth should be multiplied with respective area to convert it to volume. This is the major step here. So if you go wrong in multiplying the coefficient and the conversions here, if you directly multiply and if you directly use that same depth value, you go wrong because the other values are in terms of volume. So the runoff volume is calculated using the water budget equation. So the next part here is we had mentioned the different methods of flood estimation as unit hydrograph and probability method here. So before moving on to unit hydrographs, I'll just finish the probability method and how frequently how probable the flood occurrence would occur over the years, and how it would whether the flood frequency or the higher intensity value or the storm duration is continuous over the successive period or not. So we'll go for the probability method first, and then we'll take up the unit hydrographs. So flood frequency and probability. So I have taken a simple example here. Assume there is a precipitation, that is higher precipitation of 30 centimeter depth, and say that this rainfall magnitude occur at least once in 10 years. So if they say that at least this precipitation value occurs once in 10 years, we cannot say that in another 30 years it would occur 3 times. We cannot say that probability. Some might be at 11th year, this precipitation might not occur itself. Or in the 20th year, this precipitation might be huge. Or in the consecutive years, it might also occur at the 12th year and the 11 and a half year also. So this probability, you cannot say fixed value. So there comes the important terms, return period. So where this, the rainfall magnitude which occurs once in 10 years. So 10 years is nothing but the return period. So return period is nothing but is the average time interval between the occurrence of the rainfall magnitude, which is equal to or in excess of the specified magnitude. So this is return period. 10 years is nothing but return period, which is denoted by T. The next is probability P. So how to calculate probability is reverse of return period. that is 1 by T, gives directly the probability of occurrence. So the probability of the rainfall whose magnitude is equal to or in excess of a specified magnitude having a return period T occurring in a given year. For that particular year, how frequently or what is the probability of its occurrence is directly calculated by 1 by T. The next is Q, small q, probability of rainfall not at all occurring in a given year. So it is not compulsory that here in the same example, this rainfall magnitude occur at least once in the year. It is not compulsory that it has to occur. So sometimes it might not. So what is the probability of not occurring in a given year is calculated as Q is equals to 1 minus P, where P is nothing but the probability. You calculate it as 1 by T. The next is the probability of rainfall occurring R times in n successive years. It is not compulsory that it has to occur only once in the year. So, or it doesn't mean that it should not occur again in the next consecutive year. So how many times it would occur in the n successive years, which is calculated as PRN is equal to NCR P to the power of R Q to the power of n minus R, where NCR is given as n factorial by n minus R factorial into R factorial. So R is the number of times it is occurring, n is the successive years. So the next is the probability of rainfall not occurring at all in n successive years, which is also known as reliability. So in the successive years, say for 10 successive years or for 5 successive years, if it is not at all occurring continuously, then how do you calculate its reliability? So the reliability is calculated, is given as Q to the power of n. The last part is the probability of rainfall occurring at least once in n successive years. You say that at least it appears once in the mentioned years. Say for 10 successive years, it at least be the precipitation is obtained at least once in that 10 years. Then it is called as risk. So risk is calculated as 1 minus Q to the power of n. So you have to remember at least these steps to calculate. Then you can easily crack any type of question related to probability and frequency. So you have to know which is the return period is, how to calculate the probability of its occurrence. You should know when, if, what is the probability of not occurring in a given year, how to calculate its probability of occurrence in n successive years, and risk and reliability factor. So I have taken one example here. So there are, in the same example, I have taken 3 different cases. I'll read out the question. On the basis of rainfall map of 50 years, 24-hour maximum rainfall in Delhi is found to be 16 centimeter. Find the probability of a 24-hour rainfall of magnitude equal to or greater than 16 centimeter occurring at Delhi. So what is the condition here? There are 3 different conditions here. So first condition says as once in 10 successive years. So that is this 16 centimeter data. Similarly, I have taken here as 30 centimeter, but here it is said as 16 centimeter. So here the probability of occurrence was 10 years. Here it says as 50 years. That's the only difference. So the first thing we have to calculate is what is the probability of occurring at least once in 10 successive years. The second one is twice in 10 successive years. The last one is at least once in 10 successive years. So what are the data we have? We know that this 50 years is nothing but the return period. And this 10 successive years everywhere, it is nothing but n. If I go back here, if I go back to this here, see which formula to adopt. So if you go to this part, the probability of rainfall occurring R times in n successive years. Now for the first condition, he says it occurs 1 time. The second condition, he says it occurs 2 times. The last condition, he says at least once in 10 successive years. That is the last part, which is nothing but your risk. The probability of rainfall occurring at least once in 10 successive years. Okay. So with this, with the same formulas, I'll take up one by one, first condition by the next, so that it is very easy to understand. So we know what is return period is. Once you know the return period as 50 years, calculate the probability. How to calculate probability? Probability is given as 1 by T. So when you substitute the value, you get P as 0.02. Now, once you know the probability, we'll take up section by section. The first section says once in 10 successive years. So what happens to the formula here? If I go back, what happens to the formula here? That means R is 1, N is 10. So that is what I have substituted here. So R is 1, N is 10. So what is the probability of its occurrence? You substitute in the value formula here, NCR, P to the power of R, Q to the power of N minus R, where R is 1, N is 10. So you substitute the value here. And how do you calculate NCR value? NCR value is nothing but N factorial by N minus R factorial into R factorial. N factorial is in the sense 10 factorial divided by N minus R. 10 minus 1 is 9 factorial into R is 1. So 1 factorial. So if you calculate the value and substitute, the probability of occurrence is 16.67%. So there are chances of 16.67% chance of occurring this value, that is 16 centimeter rainfall in 10 successive years, at least once. And what is this probability? It is 16.67 chance, 16.67% chance. Similarly, in the same way, we take up the second condition here. The second condition says twice in 10 successive years. So that means we are using the same probability equation, where twice in the sense R is equal to 2 and N is equals to 10. In the same manner, we calculate what is the probability of occurrence. So probability of occurrence is given in this, by the same formula, where N is equal to 10 successive years. So 10. R is twice in 10 successive years, and hence R is equals to 2. So you adopt the same procedure. Again, 10C2 is calculated in the same manner as we did in the previous case. When you substitute the value, the probability of occurrence twice in 10 successive years is 1.53% chance. Okay, so I hope you have understood. So here we are using the same formula, but R value is changing. But the last part, at least once in 10 successive years, it is a risk taking. At least we say that it at least occurs once. We are fixing that it at least occurs once. So what is the risk factor? How do you calculate the risk factor? That is the last formula, 1 minus Q to the power of N. Okay, so how to calculate that 1 minus Q to the power of N? How to calculate Q? Q is nothing but 1 minus P. We already know what is the probability. Probability is 0.02. So you calculate that Q value and you calculate risk. So what is the risk of occurrence of this 16 centimeter depth of rainfall in Delhi at least once in 10 successive years? 18.29% of chance. So this is how you have to calculate. So here we have included everything. So most of the cases have included, all the 3 cases here have included. That is the same probability equation, where it occurs at least once in 10 successive years, where it occurs twice in 10 successive years, and the risk factor. So the other possibility of asking the question is, we have covered here of how to identify the return period, how to calculate the probability if the return period is known, and how to calculate the probability of rainfall occurrence not occurring in the given year, that is Q. With Q value, we are calculating it. We are calculating the risk factor at least once in n successive years. They might also ask the reliability factor, which is nothing but the probability of rainfall not occurring at all in the n successive years. In the same question, if he says, what is the probability of not occurring at all in 10 successive years, then it comes to reliability factor. I hope you have, I have cleared all the conditions here. So this is the probability and the frequency factors. This is the most commonly asked in the GATE exam. And most students, they don't attempt this question because it's related to some probability. So if you remember these steps, everything you have to just, remember the formulas and what is the case given in each question. If you very well analyze the situation asked in the question and the formula you adopt, it is very easy. Okay, so the sentence which is marked in pink color, you have to remember the cases. What are the different cases could be asked in the sub conditions? So according to that, you have to adopt the condition. So there is only 3 factors. If it is occurring R times in n successive years, you have to go for the factorial equation. Otherwise, you have other 2, that is reliability and risk. This is related to the probability and frequency of occurrence. The next here, I have given one question. I want you people to take up this question. You solve it in the same manner. The same what I have done in the previous case. I want you to take up this question. I'll read out the question. A 1 hour rainfall of 10 centimeter magnitude of a station has a return period of 50 years. The probability that a 1 hour rainfall of magnitude 10 centimeter or more will occur in each of 2 successive years. Okay. So here, what is the rainfall depth? 10 centimeter. And what is the return period? 50 years. So it is the same manner. It is the same manner. I want you to calculate this, and please put your answers in the chat box so that I can go through your answers and verify which is correct or wrong. Okay. So please resolve this. I'll just give you a few seconds of time to note down these values here in the question, and then I'll move forward with the next topic. Okay, I hope everyone have taken this question. I want you to solve and put the values in the chat box. So the next part is hydrograph. So hydrographs, it is nothing but a graphical variation of the discharge with respect to time at a particular point on the stream. So all of us, we know the definition of hydrographs, but most students, they don't attempt because it seems to be very lengthy. I would say it is very easy. I'll teach you how to resolve even the S-curve method very easily, and what are the hints you have to follow, and what is the type of question they would ask, and what are the hints you have to follow to resolve those type of questions. Okay, so here with the hydrograph, what are the different segments you have to know that majorly they would ask related to something related to components of hydrograph. The components of hydrograph is nothing but your rising limb, and then you have the crest segment, and then you have the recession limb. So what is this rising limb? Rising limb, it mainly depends on the duration, intensity of rainfall, and the time area diagram of the overland flow. Okay, so whereas this crest segment, which gives the peak discharge here. So that is nothing but the high discharge with respect to time in the given catchment area. And then the last one is a recession limb. That is the falling limb. It is also known as falling limb. So there are various factors which affect this hydrograph, maybe shape and size of the basin, either the wind of the effect of the wind, or the direction of a storm, rainfall intensity, the duration of its occurrence, and also soil moisture conditions. So there are various factors which affects the hydrograph. The one important thing you have to know that each component in this part, that is what do you mean by discharges, we all know, because hydrograph is nothing but discharge versus time. Correct? So we should be knowing what is discharges, and then what is this rising limb. Rising limb is also known as the concentration curve. So it nothing but it reflects a prolonged increase in the discharge. You can see here, it nothing but it shows the increase in the discharge until it reaches its peak. Okay, so the next one is peak discharge, which is nothing but your crest segment. So peak discharge is the highest point on the hydrograph when the discharge is the greatest point at its peak. So here is the crest segment. So peak discharge is the discharge at the highest value. So the next is recession limb or the falling limb. So this recession limb extends from the peak flow rate to the downwards. So it represents the withdrawal of water from the storage built up in the basin during the earlier phases of the hydrograph. So you can see here itself why it drops down because of the extractions, why the discharge value is lowering down only because of the extractions. So that is represented in the falling limb or the recession limb. The next is lag time. Lag time is nothing but the time interval from the maximum rainfall to the peak discharge. So magnitude to the peak discharge value is nothing but lag time. The next is time to peak. Time interval from the start of rainfall to the peak discharge. So it is a time interval between the maximum rainfall to the peak is lag time. But the starting point of rainfall to the peak is nothing but time to peak. That is if it has started from assumed at this point, what is the time taken to reach its peak value? It is nothing but time to peak. Okay. So there are various types of hydrographs: storm hydrographs, flood hydrographs, annual hydrographs, direct runoff hydrographs, effective runoff hydrograph, and raster hydrograph. So most commonly we deal with flood hydrographs and direct runoff hydrographs. So the next thing, before moving on to the methods, I just give you the brief of why S-curve is adopted. That is nothing but summation curve hydrograph. S-curve is nothing but summation curve hydrograph, which is nothing but a hydrograph which is generated by a continuous effective rainfall occurring at a uniform rate for an indefinite period. You can see here, it is continuously occurring at indefinite period. It is endless. So it is called as S hydrograph because of the shape of hydrographs that come out to be like an alphabet S. So why this S hydrograph is used? S hydrograph is effectively used to determine the cumulative values. Okay, where the rainfall values are continuously occurring over an indefinite period. It is at uniform rate. That is most important. It should occur at a uniform rate. So when to adopt this and how to calculate or how to obtain this S-curve, we'll see in the further slides. So in the unit hydrographs discussing about the methods, it is always confusion for the students that which method to adopt for the given question. There are two methods for the hydrographs, resolution of hydrographs. The one is method of superposition, and the as I discussed in the previous slide, the other method was S-curve method. That is nothing but summation curve method. So when to adopt superposition method and when to adopt S-curve method for the given numerical problem. Okay, so in the given question, they'll mention what is the unit hydrograph time duration. That is, I have mentioned what you have is nothing but d-hour unit hydrograph. What you have to find is nothing but t-hour unit hydrograph. With knowing these two, what is already given and for what they've asked you to calculate the unit hydrograph, with knowing these two time data, if T by D ratio gives an integer directly, then you have to adopt method of superposition. If T by D ratio doesn't be a integer or it is a non-integer term, then you have to adopt for S-curve method. Simply, if you say T is 6 and D is 3 hours, 6 by 3 is directly equal to 2. Then no need to adopt S-curve. Whatever the value you get, you take. If assume that the value is T is 7 and D is 2, then it is 3.5. It is not an integer. Then you go for S-curve method. Okay. So how to obtain a unit hydrograph from the given flood hydrograph? Please follow these 3 steps, which is most important. I want you to keep note of all these 3 steps. The first step you have to do is you have to calculate the direct runoff hydrograph ordinates from the flood hydrograph ordinates. So the flood hydrograph ordinates would be mentioned in the numerical problem. First, we have to calculate the DRH ordinates. How to calculate DRH ordinates? DRH ordinate is calculated as FH ordinates. FH is nothing but flood hydrograph ordinate minus your base flow. Base flow would be mentioned in the numerical problem. You simply adopt this equation. You calculate what is the direct runoff ordinates. Once you find out direct runoff ordinates, the next is to find out the unit hydrograph. How to find the unit hydrograph using direct runoff ordinates is UH ordinates is equals to direct runoff ordinates divided by the runoff depth. These 2 steps are most important. So first you have to derive DRH ordinates from the flood hydrograph, and then from the DRH ordinates you have to derive your unit hydrograph. So how to derive unit hydrograph? Unit hydrograph is nothing but your DRH ordinates divided by runoff depth. Now how to calculate this runoff depth is step 3. So runoff depth is equals to volume of runoff divided by your catchment area. So this will be mentioned in the given numerical problem. So you have to follow these steps. This is most important. You have to follow these simple steps. Okay. So step 1 is to calculate DRH. Step 2 is used to calculate UH. And then step 3 is nothing but it is used to calculate step 2 only, to calculate runoff depth. Okay, so I've taken up one numerical problem here. The ordinates, I'll just read out the question. The ordinates of 6R unit hydrograph is given below. So the ordinates are given for a 6R unit hydrograph. An average rainfall of 18 centimeter has occurred over a catchment area with a uniform intensity for duration of 12 hours. The phi index of the catchment is found to be 0.4 centimeter per hour. If the base flow is 10 cumex, peak discharge of the resulting flood hydrograph of the rainfall will be dash in meter cube per second. Obviously, peak discharge, the unit is meter cube per second. Now, obviously, once they say hydrograph, I have told you there are two methods, superposition method and S-curve method. Now, how to decide which belongs to superposition method and whether it belongs to S-curve method? It is based on T by D ratio. Now, what is T by D? What is given? The ordinates of 6R unit hydrograph, which is already given. So given is nothing but D hour, that is D is equals to 6R. For what they have asked you to calculate the unit hydrograph, they have asked you to calculate a 12R unit hydrograph. So this is what the data you have to find. So T is equals to 12. So D is 6, T is equals to 12. And what is T by D? T by D ratio is 2, which is an integer. So once it says integer, obviously we have to go for superposition method. So what is the superposition method? I have taken the ordinates, time interval, that is 0, 6, 12, and 18. 6R unit hydrograph ordinates are given 0, 30, 15, and 0. Calculate at 12 hour. Correct? So first 6 and the next 12 hour. First there is already 6. We have to calculate another 6R unit hydrograph, and then we calculate what is the direct runoff hydrograph by accumulating it. So how do we calculate the very next, that is third column, that is 6R unit hydrograph, that is 1 centimeter lag. For the next duration, 1 centimeter lag. So 1 centimeter lag in the sense you bring this your 6R unit hydrograph column lagging to the next column. That is, this 0 will not come to the immediate next column. So it lags by 1 centimeter, and you simply write the values. Okay. For the 12R direct runoff hydrograph, where R is equals to 2 centimeter, because you are adding these two, that is column 2 and column 3, you are adding these two, and hence R is equals to 2 centimeter. Okay. Before they had given only 6R unit hydrograph, you have found out one more 6R unit hydrograph, so that 6 into 2, 12R unit hydrograph, how do you get? You by adding these two. Okay. So when you add it up, you get 0 plus here it's a time lag, so you get 0. 30 plus 0, you get 30. 15 plus 30, you have got 45. 0 plus 15, you have got 15, and again 0. So this is 12R unit hydrograph. How did you get this 12R unit hydrograph? Because R is 2 centimeter. R is 2 centimeter. How did you get a unit hydrograph from the DRH? We know the formula how to calculate unit hydrograph from the DRH, correct? When R is equals to 2 centimeter, we have divided this by 2 to get unit hydrograph. Why unit? Unit in the sense 1. We have got, when R is 2 centimeter, we have to convert it to 1 centimeter. How do you convert it to 1 centimeter? You directly divide this DRH by 2, then you directly get unit hydrograph. That is what is done in the last column here. So in the previous column here, that is the fourth column, we have got only DRH. The fifth column, to obtain fifth column, it is nothing but unit hydrograph. To get unit hydrograph, you divide this fourth column divided by 2. Then you directly convert 12R direct runoff hydrograph to unit hydrograph. That is, first value is 0, 30 by 2 is 15, 45 by 2 is 22.5, 15 by 2 is 7.5, and 0. I hope it is clear. Okay, so this is what we have done. So what we have to follow here, we have to follow the unit hydrograph formula. How to calculate that? How to calculate that peak discharge? Here, see, they have not asked you to find out the unit hydrograph resulting flood hydrograph. So you have to calculate the peak discharge. How to calculate peak discharge? What are the data given? phi index is given, and then the base flow is given. Correct? So using those data, first I've written all the data is given. Uniform intensity of rainfall. Next, here it is important which formula to adopt. So I have told you the phi index and W index, it depends whether the given intensity of rainfall is uniform or not. If you observe here in the table here, it is whether it is a uniform or not. Here itself in the question, they have mentioned it as uniform intensity. And hence your phi index and W index will be same. So phi index is equals to P minus R divided by T, where P is already given as 18 centimeter in the question. Precipitation value is 18 centimeter already given. Runoff, the phi index value is already given 0.4 centimeter per hour. And the base flow is given as 10 cubic. So you have to find what is the runoff from that. So using this, T is at 6-hour interval, P is 18 centimeter, and you have to calculate what is the runoff from this. So once you calculate a runoff, why it is 6 again, if I go back to here, it is for the 6-hour interval they have given. You have to calculate it for the 12-hour. Okay. So if you substitute and get the what is the runoff value, 13.2 centimeter. Using this runoff value, we have to calculate what is the peak of 12-hour unit hydrograph at R is equals to 13.2 centimeter. When runoff is 13.2 centimeter, what is the peak discharge? So how do you calculate that from the previous tabular column? We have got the what is the peak unit hydrograph discharge. What is the peak unit hydrograph discharge? It is 22.5 meter cube per second. So that we have used, multiplied it with the runoff to obtain the peak of 12-hour unit hydrograph. That is 297 meter cube per second. Clear? But in the question, they have not asked you to calculate the peak of unit hydrograph. They have asked you to calculate the peak of flood hydrograph. How to calculate the peak of flood hydrograph? The first formula here. So the first formula here, the peak of flood hydrograph is equals to peak of DRH plus base flow. That is nothing but DRH is equals to FH minus base flow. Same formula we have adopted. And we have added up the base flow. Base flow is already given as 10 meter cube per second. We have added up to go at 307 meter cube per second. So here what we have done to brush it up, what we have done here is, first we have to check by T by D ratio whether it belongs to superposition or the S-curve method. This superposition, you simply lag by 1 hour duration, that is R is equals to 1 centimeter to obtain the 12-hour DRH. You divide it by 2 to directly get unit hydrograph. To the peak discharge, what you have got, the peak of unit hydrograph, you multiply it with the runoff, you directly get what is peak of DRH. To obtain runoff, you have to use the given data of phi index. So how to calculate runoff here? You know the phi index, and they have given it as uniform intensity. So phi index is calculated as P minus R divided by T. So you get what is the runoff value. Once you get the runoff value, multiply it with the discharge, you get what is the peak DRH. Once you get peak DRH, but here they have asked you to calculate what is peak FH, that is flood hydrograph. So you can use the relation that DRH is equals to FH minus base flow, or FH is equals to DRH plus base flow. Base flow is mentioned as 10 meter cube per second. So that is what we have calculated. I've taken one more here. The direct runoff hydrograph in response to 5 centimeter rainfall excess in a catchment is shown in the figure. So here the figure is given. The area of the catchment is, so you have to calculate what is the area here. The direct DRH is directly given in response to 5 centimeter rainfall excess. So how to calculate the catchment area? The formula is given as from the same steps. I have given 3 steps to remember. To resolve the hydrograph, you have to remember all 3 steps. So the last step is runoff depth is calculated as volume of runoff divided by catchment area. Now here the catchment area is what we have to calculate. So here you have to calculate first the volume of runoff. Okay, so how to calculate volume of runoff? Volume of runoff directly gives, which is nothing but the area under the direct runoff hydrograph. So how to calculate this? Catchment area is equals to area of DRH, which is nothing but the volume of runoff, area of DRH divided by runoff depth. Okay, so here it is given runoff depth is given as 5 centimeter. You have converted it to meters here. Area under DRH is given, that is volume. How to calculate it? From this peak, from this formula, from the figure here. How to calculate it? Area under the DRH. Area under DRH, it is in the form of a triangle. How to calculate the area? Half into base into height. Half into what is base? It is between 0 to 6. So base is 6 into height. Peak is up to 1 meter cube per second. So 1. So how to calculate, how did we calculate this area? Is nothing but 6. How did we get 6? It is nothing but half into base into height. How it is half into base into height? Using this figure. So from this point to end point interval is 6 and the peak is 1. Okay. So half into base into height divided by 2 divided by the runoff depth. If converted it, since it should be expressed in hectares first, we have to get the value in kilometer square, because to get the value in kilometer square, the entire value is divided by 10 to the power of 6. This is where it is important. If you directly divide the entire value by 10 to the power of 6, the value, whatever you get, it is directly in terms of kilometer square. Once you get in kilometer square, we know the relation that 1 kilometer square is equals to 10 to the power of 2 hectares. Okay. So if you multiply that 0.216 into 10 to the power of 2, you get 21.6 hectares. So this is where you have to find the relation. So we have seen that how to calculate the flood hydrograph ordinates using the DRH ordinates, and then how to calculate the catchment area for the given runoff volume and runoff depth. So the next problem here is a 2R unit hydrograph for a catchment has ordinates of 0, 3, 8, 6, 3, 2 and 0 meter cube per second respectively at 1 hour interval. Area of the catchment will be. So what will be the area of the catchment here? Again, how to calculate the area of the catchment? Runoff depth is equal to runoff volume divided by catchment area. We are using the same formula. How to calculate volume of runoff? Volume of runoff is nothing but the area of DRH. Now here, instead of giving the figure, they have not given the figure as in the previous case. So if they had given the figure, depending on the given figure, you would have easily calculated what is the area under the graph. Correct? But here they have not mentioned how it varies with respect to graph. Now, how to calculate it? It is nothing but the total precipitation data into the time interval will directly give you the volume. Okay, so here instead of depending on the area, we are directly calculating the volume of runoff. This is the other way. In the previous case, since they had given the figure, we calculated what is the area under that. So here they have not mentioned the figure, and hence we are depending on the precipitation data, that is discharge data. So we have directly calculated what is the volume. You can see here in the unit itself, meter cube per second, we need only meter cube, that is volume. So if you multiply the time, you directly convert the given value into volume. Okay, so the time interval we have converted, because it says for unit 1 at each 1 hour interval. So we have converted into seconds, because denominator in the unit meter cube per second, it is in terms of seconds. We have converted it into the total precipitation data, that is 3 plus 8 plus 6 plus 3 plus 2 is 22. We have converted it and we have got the value. Okay, so once we get the volume of runoff, we have substituted back here. And how did we decide whether the runoff depth to take 1 centimeter is, if they have, this is again the very important point. I want you people to keep it in mind. If the runoff depth or rainfall in excess is not mentioned in the numerical problem, always whenever say unit hydrograph, it is always R is equals to 1. Unit hydrograph R always is equals to 1 for the unit hydrograph. That is why the name itself says unit hydrograph. If not mentioned in the given numerical problem, R is always equal to 1 centimeter. That's why I have taken directly runoff depth, that is 1 centimeter, is 0.01. When you substitute it, the value we get is 7.92 kilometers square. I hope it is clear. So there are different issues we had discussed where the graph was given and you calculated area instead of volume. And even the runoff excess was mentioned here. But here in this numerical problem, again, there is no figure, but we have calculated volume directly. And rainfall excess is also not mentioned. And hence, we have directly taken runoff depth as 1 centimeter because it says unit hydrograph. This is one. Now moving on to the next question here. A 2-hour unit hydrograph for a catchment has ordinates of 0, 3, 8, 6, 3. To same problem have taken. In continuing with the same problem, a storm of 8 centimeters occurs over the catchment in 3 hours. If the phi index is found to be 2.5 millimeter per hour, the peak flow due to the storm will be how many cumex if the base flow is 5 meter cube per second. So once this is given, as I told you, you have to check whether it belongs to method of superposition or S-curve method. How to decide whether it belongs to superposition or S-curve method? The very first procedure is to determine what is T by D ratio. How to determine T by D ratio? You have to identify. A 2-hour unit hydrograph for a catchment is given. So 2-hour unit hydrograph value is given. So known value is D hour, that is D is equals to 2. For what hour they have asked you to calculate? For 3 hours. So T is equals to 3. T by D ratio is not any integer. So here you get the value as 1.5. So this is where you have to adopt S-curve method. Okay. So how to do the, how to follow the S-curve method is, first, 2 columns represents the given data. That is the time interval is given. He says at 1 hour interval each. So at 1 hour interval each, we have mentioned what is the direct DR unit hydrograph. That is DR in the sense 2-hour unit hydrograph data, whatever they have mentioned, we have given. Hints, whatever you have to follow is, these are the hints you have to follow in S-curve method. This is the very important 3 steps you have to follow. The first step is, that is the third column, your addition column always starts at DR, that is at the second hour. He says 2-hour unit hydrograph. If he says it is 3-hour unit hydrograph, your addition starts from the D hour, that is third hour unit hydrograph. And the value starts from 0 because the first value starts from 0. So that is what we have done here. Your addition, he says, it starts from D hour. So what is that? 2 hour. So we have started a third column at 2 hour. So we have started from 0, 3, 8, 9, 11. How did we get this? I'll tell you first. The first value is 0. So you will add up the first term, that is the summation curve for the first ordinate, SA. 0, 3 plus 0 is 3. You have got 2 extra ordinate here. So these extra ordinate is again moved to this part in the column. So 3, 8. You have got 3 extra ordinate. Now again you add up. 6 plus 3 is 9. 3 plus 8 is 11. Again you have got 2 extra ordinate here. 9 and 11. You bring it to the column here. 9 and 11. Again 2 plus 9 is 11. 0 plus 11 is 11. Then it continues that the discharge remains in equilibrium. You see here 11. At 4th hour it is also 11. 5th hour it is 11. 6th hour it is 11. So it is constant now. So how did you get this? I'll again tell this. Addition always starts at D hour. So the first value is 0. Once you write the first value, you write your first ordinate. The first ordinate is adding up the second column and the third column, 0, 3, and 8. Then you have got, till up to this point, you have got only 2 extra ordinates. You bring that ordinate to this third column, 3 and 8. And then again, you add up column 2 and column 3, that is 6 plus 3, you get 9 and 11. Again, you have got 2 extra ordinates. You bring it to the third column and again you add it up. How to get the fifth column is the second. Addition, SA, SB, all the values are same. These all values are same. You can see here 0, 3, 8, 9, 11, 0, 3, 8, 9, 11. All these values are same. But SB, that is your fifth column, always starts at T hour. This is where it is important. You have to remember the first step and the third step. So your T hour, that is the fifth column, SB, it always starts at T hour. So TR in the sense 3 hours. So at the third hour, the value starts from 0. So 0, 3, 8, 9, and 11. Okay. So how did you get this unit hydrograph? Unit hydrograph is directly obtained from at R side, R value. What is the R value you have got? T by D ratio, it is nothing but it's 1.5. So before there in the previous problem we had solved where R was 2 centimeter. To get the unit hydrograph, we divided it by 2. The integer was 2. Correct? So here the integer, it is not an integer, it is 1.5. So each value has to be divided by 1.5. So 3 divided by 1.5, 8 divided by 1.5. We have divided all the values by 1.5. Okay, so that is 0 minus 0, 3 minus 0 is 3, 8 minus 0 is 8, 9 minus 0 is 9, 11 minus 3 is 8 by 1.5, 11 minus 8 is 3 divided by 1.5, 11 minus 9 is 2 divided by 1.5, and the last value is 0. So once we get that, so peak of 3R dr but 6 into R. Why is 6 into R? 9 by 1.5 is nothing but 6. We are calculating this peak. That is why it is in red mark. We have calculated only for the peak. If you see here, what is the peak value? 9 divided by 1.5 is the peak value. That is what we have calculated. So how to get the runoff value? At what value you have to calculate that peak? At runoff value. So runoff value is not given here in the numerical problem. They have given only the phi index here. So how to calculate the runoff value? Again, you have to see what is the uniform intensity here. So phi index is equals to P minus R by T. P you have to calculate. Minus, here they say a storm of 8 centimeter occurrence. So this is what you have to calculate, the runoff. So P is 8 centimeter minus R divided by at 3 hour interval, so 3 hours. So phi index is given as 2.5 mm, so 0.25. So R is equals to 7.25 centimeter. So if you multiply this this R value into the peak discharge, you directly get what is the peak discharge of DRH, peak of DRH. How do you obtain peak of FH? Using that in the same formula. Peak of DRH plus base flow. Peak of DRH is obtained from the previous, that is 43.5 plus your base flow. Base flow is 5 meter cube per second. You end up with 48.5 meter cube per second. Okay. So the last part is equilibrium discharge. Here, what do you mean by equilibrium discharges? In the previous case here, you can see equilibrium discharge is nothing but 11, which is a constant value. It is nothing but equilibrium discharge. Okay. So sometimes they might ask you to calculate this equilibrium discharge for the given precipitation value directly. You no need to adopt for S. Sometimes calculate the peak discharge according to the given condition. Then, if not mentioned, how to calculate this peak discharge value, that is nothing but the equilibrium discharge is given by the formula 2.778 A by D. Okay, so I have taken the same example in the previous case here. For the same data, in the previous case, we have calculated what is the area here. For the same numerical data, we have calculated what is the area here. That is 7.29. And what is the D hour? That is 2 hour interval. The same formula, for the same formula, I had given the continuation here. So substituting that term here, that is 2.778 into A value is 7.92 divided by 2. So which gives 11 meter cube per second. You can see here, which is nothing but your equilibrium discharge. Okay. For sometimes for the given area and the precipitation data, they might directly ask to calculate what is the equilibrium discharge. So in that case, you can adopt this formula where 2.778 A divided by D. You have to note that A is in kilometer square units and D is in hours. Okay. So with this, we have completed flood routing. The last part which was left out in the hydrology is groundwater hydrology part. So here the groundwater hydrology. So we have a different the classifications of the zones: zone of aeration and zone of saturation. Again, in zone of aeration, we have three different zones: capillary zone or pellicular or intermediate water zone and soil water zone. What is zone of aeration? In this zone, the soil pores are partially filled with water. The space between the ground surface and the water table is the zone of aeration. You can see in the figure here itself, zone of aeration, the first part. So in zone of aeration, again, we have three categories. That is soil water zone, intermediate water zone, which is nothing but pellicular zone, water zone, capillary fringe. So soil water zone, it is adjacent to the ground surface consisting of the top soil and the subsoil. The depth of this zone varies up to 15 meter depending upon the type of the soil. So in the intermediate water zone or pellicular zone, this zone lies between the soil water zone and the capillary water zone. So the water in this zone is also known as Vadose water. The next is capillary fringe in the zone of aeration. This is the zone in which water is held by capillary action. So the name itself says capillary fringe, where the water is held by capillary action, is situated between the gravitational zone and the saturated zone. So the last one is zone of saturation. So here the voids are completely saturated with water. So this zone may include loose, unconsolidated deposits of sand and gravel, as well as porous rock formations like limestone and sandstone. These are the classifications of subsurface. The next important thing is geologic formations of aquifer. They might ask the MCQs related to this part. We know there are four types, that is aquifer, aquifuse, aquiclude, and aquitard. Now, what is the difference between these geological formations? Aquifer is a permeable geologic formation that stores and transmits water. Fuse is the rock formation containing no interconnected openings, and therefore neither it transmits nor stores. So aquifuse, it neither transmits nor stores. Aquiclude is a formation of rocks which can store water but cannot transmit. So you can see here in the picture itself. So aquiclude, it can store water but it cannot transmit. Water and cannot transmit. So you have to be very careful in the differences between these geological formations. They would ask this either in the form of match of the following or to find the odd one out, giving the definitions. So we have four geological formations: aquifer, aquifuse, aquiclude, and aquitard. So if you remember this tabular column, it is very easy. Sometimes they might ask even the examples also. So this shows the types of formation, its hydraulic properties, as well as the example, whether it stores, it transmits, whether you get the yield, and what is the example for that. Okay, so aquifer, as I said, it stores and transmit, and the example is sand and gravel. Aquiclude, it stores and does not transmit clay or shale. Aquitard stores and transmit, but the yield is very slow or very less, and the example is clay. Aquifuge, it neither stores nor transmits, and hence there is no yield, granite and basalt. The next important topic here in the groundwater hydrology is types of aquifers. We know there are two types of aquifers: unconfined aquifer and confined aquifer. So what is unconfined aquifer? Water table aquifer, which is also known as free water surface, where free water surface exits. So unconfined aquifers are also known as water table aquifer. So recharge to this aquifer takes place through infiltration of precipitation of ground surfaces. So a well which is driven into this water table aquifer will indicate a static water level corresponding to the water level at the location. So next is confined aquifers. Sometimes it's also known as artesian aquifer and leaky aquifer. This is where a question was asked when it was called a leaky aquifer. So confined, as the name itself says, it is confined between the two impermeable beds, such as either it may be aquicludes or aquifuges. So the recharge to this aquifer occurs only in the area where it is exposed to the groundwater surface. So the water in the confined aquifer will be under pressure, and hence the piezometric levels will always be much higher at the top level of the surface. And hence the well driven into this aquifer will flow very freely without any aid of pump. So confined aquifers, it is also known as leaky aquifers if either or both of the confining, that is impermeable beds, are aquitards. Either one or both the impermeable beds are aquitards, then the confined aquifers is also known as leaky aquifers. So what are the different properties here? You have to know the different properties. One is porosity. How do you calculate porosity? It is nothing but the amount of pore space per unit volume of the aquifer material. And how do you calculate it? VV by V naught, which is nothing but volume of voids by volume of porous medium. If porosity is greater than 20%, it is considered as large. If the value is between 5 to 20%, it is medium. And if it is less than 5%, then it is small. The next is specific yield and specific retention. These are all the formulas you have to keep in mind to easily crack the questions related to aquifers or groundwater hydrology. So the actual volume of water that can be extracted by the force of gravity from a unit volume of aquifer material is nothing but specific yield. And what is specific retention? It is nothing but the fraction of water which can be held back in the aquifer. So N porosity can be calculated as SY plus ST, which is nothing but the summation of specific yield and specific retention. The next is transmissibility T. It is defined as the discharge through an aquifer of unit width and thickness B under a unit hydraulic gradient. So T is equals to K into B. These all relations you have to be very careful while using it, because most of the numerical problems, they give direct values in terms of groundwater hydrology. They give direct values. You only have to remember these formulas to substitute. So transmissibility is equals to K into B, where K is nothing but the coefficient of permeability and B is thickness of the aquifer. And what is a unit? It is either meter square per second or meter cube per second per meter, which leads to meter square per second. So the next is storativity. So storativity is nothing but the volume of water released by the column of confined aquifer of unit cross-sectional area and a unit decrease in the piezometric head. So to calculate storativity, it depends of which type of the aquifer is, whether it is confined or unconfined. You have two different formulas to adopt for confined aquifer as well as unconfined aquifer. For confined aquifer, storativity is calculated by the unit weight of water into porosity N into beta value plus alpha into B, where beta and alpha is nothing but the beta is compressibility of water and alpha is nothing but compressibility of the formation material, and B is the thickness of the aquifer. Whereas the storativity for unconfined aquifer is calculated by this formula: specific yield plus unit weight into alpha plus N beta into B. This is the difference in the formula. If in the given question it is confined or unconfined, you have to adopt the formula accordingly. So you have to be very careful that which type of aquifer is asked, whether it is confined or unconfined. So here I have taken a simple numerical problem. An undisturbed rock sample has an oven dry weight of 0.655 kg. After saturation with kerosene, its weight is 0.0732 kg. It is then immersed in kerosene and found to displace 0.301 kg. What is the porosity of the sample? Now, how to calculate porosity? Porosity is the weight of kerosene which is required to saturate the given sample divided by how much of it is displaced. So how much is required divided by displaced, you directly get what is the porosity. Same as your laboratory component, how we have done in the laboratory calculation of porosity. Your dry weight minus your saturation divided by displacement, you directly get what is the porosity. So how did we calculate it? Weight of kerosene required to saturate the sample divided by weight of kerosene displaced by the saturated sample, which is nothing but, see here, after saturation, the kerosene weight was this much. So before that, the oven dry weight was this much. So how much is required? You get W2 minus W1, you get how much is required. So numerator you have W2 minus W1 divided by this is the amount of kerosene which is displaced, that is 0.301 after saturation. So that is W3. So porosity is 0.655 minus 0.0732 divided by 0.301. It is measured in terms of percentage. If you multiply the value into 100, you get 25.58%, which is nothing but your option D. Which is nothing but your option D. Okay. So there is one more example here. When 3.68 million meter cube of water was pumped out from an unconfined aquifer of 6.2 kilometer square aerial extent, the water table was observed to go down by 2.6 meters. The specific yield of the aquifer will be. Okay. So here you have to know that there is some amount of water which is pumped out in the aquifer. So how much was released should be equal to the amount of water pumping out. So this is the basic equation. Amount of water released should be equal to amount of water pumped out. So now what is the amount of water which is released? So you can see at what is the aerial extent? 6.2 kilometers square, and what is the depth? 2.6. Correct? So this is the volume of water released into its yield will give you what is the amount of water which can be pumped out from the same area. What is the amount of water which is pumped out? That is 3.68 million meter cube. So if you substitute, it directly gets specific yield. Since the value is in percentage into 100, you get 22.83. That is option D, 22.8. Okay, this is the other way. Not obviously you have to follow the unconfined aquifer conventional formula where you have to know what is beta, alpha, and everything. Okay, if you simply adopt the concept that how much was released and how much was pumped out, the amount of water which is released should be equal to amount of water which has to be pumped out, then you directly get or directly easily calculate what is the specific yield. So here there is one more problem. In an alluvial basin of 200 kilometers square and 150 megameter cube of groundwater, which was pumped out in a particular year such that groundwater table dropped by 5 meters. Assuming no replenishment, the specific yield of the soil is how much? So you have to calculate this. It is the same manner. See here, area is given. The volume of water which was pumped out is given. And the depth of water is given. You have to calculate the specific yield in the same manner. Amount of water released is equals to amount of water pumped out. How do you calculate amount of water released? That is area into depth into specific yield will give you amount of water which is pumped out. So you have to calculate this and tell me what is the specific yield value you get, either option A 3 or option B 6. C9 or D15. Please solve this and put the answer in the chat box so that I can verify whether the answer is correct or wrong. I'll give you a few seconds here to just note on the values. So area value is 200 kilometers square. The volume which can be pumped out is given as 150 megameter cube. The specific yield of the soil. Okay. So there is a question from Shweta. In the empirical formula for flood estimation, let me go to that slide quickly. Okay, in the empirical formulas here, yes. In the empirical formula for flood estimation, do we have to remember the value of constant for various catchments? Here, they'll give the constant value. So in the empirical formula here, they'll give all the constant values here for the given specific region. So you don't have to remember. They'll give the area and the constant value. You have to calculate directly the peak discharge for the given area, for the given region. Okay, so the constant values they'll mention in the numerical problem. Again, if T by D value is an integer, yet in DR unit hydrograph, the time interval is not same as DR. In that case, how to apply method of superposition? I didn't get you. I'll just go to this part if it helps. See, the difference here is, I hope, yes, even let's see, the time interval is not same as DR interval. Okay, so you mean to, I assume you mean to say that this 0-6 is 6-hour interval and 6 to 12 is same. Okay, here also we have adopted uh, T by D. And in that case, in the second case here, see in this case, here if that is what it is important. If T by D ratio, if it is of same equal interval, you'd obviously get the method of superposition. Okay, if it is in equal intervals of time, that is how one hint to follow up. If it has equal interval of time, you can directly go to superposition method. No need to solve through S-curve method, because it always gives an integer if it is an equal interval. If you can see here, the intervals here is also a single same thing. Okay, so here in the 6-hour interval, but here it says each 1-hour interval. There it was 6-hour interval. Here it is each 1-hour interval. But when you do the ratio T by D, it will not give you an integer. It gives 1.5. This is where it is important. Not always, if you get the same interval as DR, you would go to superposition method. Okay, sometimes even the interval between the each ordinate is same, it would not give an integer. It depends on what unit hydrograph they have asked for, what is the time interval they have asked for, and what is given. I hope it is clear. Okay, so I'll just move on. I'll just move on. Okay, so I want you people to solve this numerical problem. Please take up the area and the volume and please calculate and put your values. I hope Shweta can do it. Please take this value and please calculate the specific yield value, and you can put the value in the chat box. I'll just cross verify your answer. So the next important thing is Darcy's law. We all know the Darcy's law, how to calculate the discharge. And we know that Darcy's law is applied for laminar flow, and hence the Reynolds number should be equal to 1. And the next important thing here is the wells. So this is where the most of the problems would be asked. Here you have to remember the discharge equations for both confined and unconfined aquifer in the steady flow conditions. So here we have different well loss conditions. There are 3 conditions. One is formation loss, one is loss due to a drop in piezometric head, and the other one is head loss. So the total well loss is calculated as C1Q plus C2Q square, where C1Q represents the formation loss and the second term represents the well loss. Okay, you have to calculate. There might be a question related to this part also. C1 and C2 constants will be given for a condition. For the given well, they'll give the values of C1 and C2. So you can easily calculate what is the well loss, total well loss. Okay. So again, what is recuperation test? Recuperation test is nothing but a recovery test. What do you mean by recovery test? Once you pump out the water, there will be drop down in the water table. Okay, so once you stop the pumping of water, gradually that water table gradually it increases. Okay, so that increase of water table level gradually is nothing but your recuperation test. Okay, so what is the time duration for any water table to get to its recovery level is calculated by using this formula, which is nothing but the time duration for recovery is nothing which is calculated from the recuperation test. So this is the formula which is adopted. That is TR, which is nothing but the time for recovery, is equal to A by K naught and H1 by H2. H1 by H2 is the head levels or the water table levels before and after the recovery. Okay, so here it is most important. One is confined aquifer and the other one is unconfined aquifer. These are the formulas you have to remember for confined and unconfined aquifer. Thames equation, that is Q value, Q formula which is given, Thames equation. And the other one, when the drawdowns are known, S1 and S2, and when it satisfies wall conditions. All these three gives discharge itself, but for the three different conditions. Again, for the unconfined aquifer, the same Thames equation, that is nothing but your equilibrium equation, how to calculate Q value and when it satisfies your well conditions. Okay. So these are the different discharge forms. How you can use the same formula depend according to the given condition. Okay, you please go on to the slides again so that it is easy for you. If you take up a problem, if you go back to these particular slides, it is very easy for you to analyze. Clear? So here there is a problem. I quickly go to the problem. I'll show you how to resolve it. Yes, I see Hiteshi has solved the 15%. Yes, the specific yield is 15%. Yes, correct. Very good. An unconfined aquifer is pumped at a constant rate of 10 LPS. Steady state drawdowns measured at the radial distance of 30 meters and 60 meters are 0.8 meters and 0.7 meters respectively. Original thickness of the aquifer is 30 meters. The transmissibility of the aquifer is. So you have to calculate the transmissibility. Here I have used for an unconfined aquifer the discharge equation when the transmissibility is given. This is the formula I have adopted. So instead of using LAN, I've gone directly to the base 10. So multiplied with 2.3. This is the relation I have given in the previous slide. You please go back and check it. So I have substituted all the values S1, S2, R2 and R1. If you substitute it where Q is 10 LPS, you have to convert it because it should be in meter cube per day, because you can see the value is in meter square per day. Correct? So you have to convert this liters per second to meter cube per day. Then when I substitute it, all the values, you get T is equals to 952 meters square per day, which is nothing but your option C. Okay, this is as the same thing. With radius 0.5 meters, completely penetrates an unconfined aquifer of thickness 50 meter and K is 30 meter per day. The well is pumped so that water level in the well remains at 40 meters above the bottom. Assuming the pumping has essentially no effect on water table at R is equals to 500 meters, the state discharge will be. This is another form of discharge equation where K value is given, that is coefficient of permeability is given, and then the pumping details are given. What is the depth of pumping rate is given. Okay, so this is the again the discharge equation. All these discharge equations are discussed in the previous slides. Please go back and see to the previous slides. You will get all the formulas. This discharge formula is same, but then depending on the given data, the relations change. That's it. Okay, so these are the given data where K is 30 meters per day, H is 50 meters, HW is 40 meters, R is 500 and RW is 0.5. If you substitute, you get 142.12 LPS, which is nothing but your option C. Okay, so I'll quickly move on to the irrigation part. That is nothing but your water requirements of crops. It will hardly take 5 minutes. So irrigation, the main thing they ask in the irrigation, you know why irrigation is required and other stuff and what are the different sources of irrigation. The one thing they would ask is the frequency of irrigation. The frequency of irrigation is 3 days. This is most commonly asked question. And why the irrigation is adopted majorly because of the insufficient rainfall, uneven distribution of rainfall, improvement of perennial crops, development of agricultural in desert area. Because of all these necessities, we have gone for irrigation. Once we say irrigation system, it has both benefits and ill effects. Some of the benefits I have listed here. And there is also the benefits and the advantages also comes along with the disadvantages. The raising of water table, it is also leads to the formation of marshy land, dampness in weather and other stuff. Okay, so this is the classification of classification or the availability of soil water zone. We have hygroscopic water, which is capable of movement by the gravity or the capillary force. Just we have capillary water at this time. The next is the important term, that is field capacity and wilting point, which is both used to calculate the water stored. So how to calculate the depth of water stored in a given catchment area is using your field capacity and the wilting coefficient. Okay, so dW is equals to dry weight divided by unit weight of water into D, which depth which gives you what is the depth of water stored. Okay. So next is what is the time to irrigate a given land. So T is the formula. All these irrigation is basically depends on the formula. So T is equals to A into dW by Q. So it depends, dW is nothing but the depth of water in meters, Q is the discharge in the field channel. Okay. So what is the time taken to irrigate a given land? Whether it may be either in seconds or hours. So this is the relation. If it is in seconds, if the value or the options given are in seconds, you can directly go for this first formula, or if it is in hours, you directly go for this formula 2.778 A into dW by Q. Okay, so you know the various classification of crops. I don't want to go to the theory part. I'll say the important topic is crop ratio. The ratio of proposed area to be irrigated in Kharif season to the Rabi season. Crop period is total time that elapses between the sowing of crop to its harvesting. These two are important. They'll ask the question related to crop ratio and crop period. Okay, this is the important thing. Duty, delta, and base period. I'll quickly go to this. You know the formula here. So duty D is represents the irrigating capacity of a unit of water. Delta is total depth of water required by a crop during the entire period of the crop in the field. Base period is time interval between the first of watering to the crop to the last watering. So here the formula between the duty and delta relationship is delta is equals to 8.64 B by T. So this is important. Okay, so I'll quickly take up one numerical problem. A tube well having a capacity of 4 meter cube per hour operates for 20 hours each day during the irrigation season. How much area can be commanded if the irrigation interval is 20 days and depth of irrigation is 7 centimeters? So we have the relation delta is equals to 8.64 B by T. So this is B is 20 days, delta is 7 centimeter. If you calculate, we get what is the duty, that is D is equals to 8.64, 20 divided by 0.07, which is nothing but 2468 hectares per meter cube per second. That is hectares per cumets. Okay. How do you calculate discharge? How do you calculate the discharge? So what is the capacity? Well, capacity 4 meter cube per hour into for how many hours it is running up? It is operating for 20 hours. For 1 hour, it is 4 meter cube. For how many hours it is operating? For 20 hours. So 4 into 20, the discharge is 80 meter cube per day. And how do you convert it meter cube per second? When you convert it, do the conversions of time here, day to seconds, you get 9.26 into 10 power minus 4 meter cube per second. So how do you calculate the area here? A is equals to D into Q, which is nothing but you know the relation Q is equals to A by D. That's the relation we are using here. So area is 2.29 to 10 power 4 meters square. The same thing. Okay, duty delta relationship. So the next is if duty D is 1428 hectares per cubic and base period B is 120 days for indicated, what is delta? This is directly given. D is given, B is given, you have to calculate delta. That is 8.64 B by D. If you use the relation, you can easily calculate what is delta. If you very quickly note down what is D is equals to 1.1428 and B value, you can solve. The next one is simply they would ask related to gross command area and cultural command area. The culturable command area is again, it can be cultivated or unculturable. Okay, so the relation is GCA is equals to CCA plus unculturable. So there are various efficiencies which is involved in the irrigation. So these are all the formulas. I want you to please go back to the slides and just cross verify all the efficiencies and other stuff. So these are the main topics in irrigation which they would ask. Okay, based on only duty delta and all these efficiencies. This is a simple problem where the efficiency is calculated, where you have to calculate the efficiency of application. Okay, please go through all these things. So these are all the direct formulas. I want you to go through all these things. Okay, so the efficiency is, every efficiency formula is given. It is very simple, and how much you apply, how much is retrieved, how much is stored, how much is needed. Depending on that, you calculate the efficiency according to the given name itself. Okay, so one simple problem where the efficiency of application is calculated. Please go back to the slides and you can easily track it. If you still have any doubts, you can simply contact your queries. Okay, I hope it is helpful. Thank you, audience, for your patience listening. If you have any queries, please you can post it in the chat box. I'll be helpful for you to answer those queries. Thank you again. Over to you, Rajit sir.
Thank you, Professor Madhushree. It was a very informative session. So I request a participant to fill the feedback forum. You can find the feedback link in the YouTube chat box. And I request all the participants to join today's second session at 3:45 p.m. using the same YouTube channel. Thank you.